Good morning, students. So today in theory of computation class, we are going to discuss about finite automata. So before entering into the subject, first we should know about the automata theory. So automata theory means it is a study of abstract computing device or any machines, which means we are going to study the abstract computing devices and machines, abstract model of the computing devices and machines here. So automation, which means nothing but the abstract computing device. So here we should note that a device need not even be a physical hardware. It should be a software also. It may be a software also. So in this, we are discuss about the theory of a computing machine, which means we are going to study about the software, automation of our software. A fundamental question in computer science. Find out what different models of machines can do and cannot do. So the answer is our theory of computation. So coming to the language. So before we study about the finite automata, so we should know the basic concepts. So the basic concepts of our finite automata. The first concept is our alphabet. So what is alphabet? An alphabet is a set of symbols. So alphabet is a set of symbols. The symbol means it may be a numerical symbol or it may be a alphabets like A to Z, or it may be a special character like plus, minus, star, slash, etc. Okay. So alphabet is nothing but a single symbol. In a alphabet set, no, we have a set of symbols. Okay, so in any language, no, it may be a English or whatever the language, we should know about the alphabet. Then only we can form the word, and then only we can form the sentences, and finally we can form the paragraph or language, whatever it is. The basic thing is the basic symbol is nothing but the alphabet. So here alphabet means it may be a numerical value 0 to 9 or A to Z, small a to Z or capital A to Z, and then all type of special characters. All those things are comes under the alphabet concept. Okay, the curly braces, no, which is used to represent the alphabet. So here, see the example within the curly braces, we are using 0, 1 here. So here 0, 1 is the alphabet. So now coming to the next concept. Next important concept is nothing but the string. The other name of string is the word. So word means how can we form the word from the alphabet? That is combining more number of symbols. That is nothing but the collection of alphabets. Collection of alphabet is known as the strings. So words or string. The other name of string is the word. So see, we have the alphabet 0, 1 here. So using this alphabet, we can form the set of words here. That is 0 is the first word, and then 1 is the second word, and then 0 is the next word or string. 0 1 is the next word, 1 0 comma etc. So we can form the n number of words from the given alphabet. So what is the other name of word? Which is nothing but the string. So the first step, first basic element is alphabet, and then the second element is using this alphabet we can form the set of strings or set of words. Okay, and then coming to the language, which is nothing but the collection of strings. So collection of strings is known as the language. So see, capital L is used to represent the language. So L equal to within curly braces, you have to mention all the strings. Okay. And then coming to the grammar. Next one, while forming the string into the language, no, we have to follow some set of rules. These rules are known as the grammar. So see here, capital S is nothing but any sentence tends to 0A, which means the particular string or particular word, it should start with 0 and then followed by any alphabet. Okay, so here don't forget alphabet means it is nothing but the set of symbols. Okay, it not only the alphabets, which means the A to Z, a small a to Z or capital A to Z. it contains a numerical value also or a special characters also. Okay, so here we have to follow the rule. This is one rule for the particular language, that is capital S tends to 0A, which means the string in particular language it should start with 0 followed by any number of zeros and ones. Likewise, in second rule, capital B tends to 1B, which means the particular language may contain the string which starts with 1 followed by B. Okay, so these are all the basic elements. So first one is the alphabet, which is the set of symbols. So using those symbols, we can combine this into a single word, which is nothing but the string. That is the second basic element of our finite automata. And then coming to the third one, a language. Language is nothing but the collection of strings. String means it is a collection of alphabet. Language means it is a collection of string is known as the language. And then coming to the grammar, which means we while forming the language, no, we should follow some set of rules. Those rules are known as a grammar. Okay, and then move on to the next one. So this is the hierarchy, the Chomsky hierarchy, which is we have four different machines, four different mathematical model, or four different ways to represent the uh, finite automata. Okay, so see here, first one is the regular languages. So regular language is a mathematical representation, and its equivalent graphical model is nothing but the finite automata. We will discuss it later. And then coming to the second hierarchy, no, it is nothing but the context free languages or context free grammar, which is the mathematical representation, and its equivalent graphical representation is push down automata, PDA. PDA means what? Push down automata. And then the third hierarchy in this, the third Chomsky hierarchy is context sensitive languages. Context sensitive languages, and its equivalent graphical representation is linear bounded automata. Linear LBA means linear bounded automata. And then the last hierarchy is recursively enumerable language. Recursively enumerable language. So, and its equivalent graphical model is our Turing machine. TM is nothing but the Turing machine. So, don't forget we have four different languages and four different models we have here. That is regular languages, and its equivalent model is finite automata. Context-free language and its equivalent model is push down automata. Context sensitive language and its equivalent model is linear bounded automata. And then the last one, recursively enumerable language, and its equivalent model is Turing machine. So move on to the next one. So here, what is language? As I said, no, language is nothing but the collection of strings over the alphabet. Okay, this is the language. For example, see here, this is the first example. Let L be the language of all strings consisting of n zeros followed by n ones. So here, this is the condition. That is, all strings in this particular language, it consists of n number of zeros followed by n number of ones. Okay, wow. So for example, I have two zeros in my language now, followed by it should have two continuous ones. That is the language. So see the language L equal to the first one, no, which is nothing but the epsilon. The symbol is known as the epsilon. So epsilon means which is the null string. Okay, epsilon means what? It is a null string value. And then see the second string. What is language? Language is nothing but the collection of strings. Collection of string is known as the language. So in this particular language, the first string is epsilon, which means the null string. That is the n value is 0 here. So 0 number of ones followed by 0 number of zeros followed by zero number of ones. It gives the output as epsilon, which means a null string. And then second string, no, I'm applying the value 1 for n. Okay, so I have 1 0 followed by 1 1. Okay, this is the second string. And then coming to the third string, no, so here the n value is 2. So 2 zeros followed by 2 ones. And then the fourth string, no, here 3 zeros followed by 3 ones, etc. This is my language. So we have to construct the language for the given statement. So what is the statement here? Let L be the language. So L equal to, you have to put L equal to, and then the condition is all strings in this particular language consisting of n zeros followed by n ones. N zeros followed by n ones. So in this, the first I apply the value 0 for n. Second one apply the value 1 for n, and then 2, 3, 4, etc. Up to n value, you can extend the language. Okay, so don't forget language is nothing but the collection of strings over the alphabet. So here what is alphabet? 0, comma 1 is the alphabet. Okay, well, alphabet means which is the basic building block of our finite automata, or any type of automata. No, alphabet is the basic building blocks. This is the basic element of our theory of computation. So here in this particular language, no, the alphabet is 0, comma 1. So L is the language. And then what about the string? String is nothing but the collection of alphabets. Collection of alphabets means in any string, no, it consists of zeros and ones alone, because we have the alphabet 0, comma 1 alone. Okay, and then coming to the language, it is a collection of strings here. So consisting of n number of zeros followed by same n number of ones. This is the condition. So based on this constraint, we have to construct the language. Okay, am I clear, Pa? What is language? What is string? What is alphabet? Okay. So what is the other name of string? Which is nothing but the word. Word is the other name of string. We know that word is a collection of characters or collection of alphabets. No? So word is the another name of our string. And then see the second example. Let L be the language of all strings of with equal number of zeros and ones. Okay, see what's the difference between previous one and then the second one? The first one, no, the same n number of zeros followed by one n number of ones. But in the second one, no, so no need to follow the same rule. That is first symbol should be 0 and then second symbol should be 1, like this. No, we no need to follow other rule. But while counting the number of zeros and counting the number of ones, no, both should be equal. That is the second language. So see, first one L equal to, so same thing, I'm applying this 0 for n. So the first string should be epsilon. Epsilon is nothing but the null character. And then coming to the second one, 0, 1 or 1, 0. So here also the count, first you have to count the number of zeros. So here the number of 0 is 1 and the number of 1 is 1. And then in third string also the number of 0 is 1, number of 1 is 1. Okay. And then the coming to the fourth one, we have 2 zeros, 2 ones. And then the fifth string note, again we have 2 zeros, 2 ones. Okay, well, no need to follow the sequence, but while counting the number of zeros or number of ones in any string of this particular language, it should be equal. That is the given condition. But in previous one, no, set of n number of zeros followed by n number of ones. So that the first set. So while dividing the string into two parts, the first part it should contain zeros alone, and then the second part it contains ones alone. Okay, that is the first language. But in second language, no need to follow the sequence. So here, while forming any string, the condition is we should count the number of zeros alone. Okay, and then number of ones alone. The number of zeros should equal to the number of ones in any string of this particular language. This is the second one, second example of language. And then coming to the membership problem, given a string W belongs to, so here we have summation symbol, no, which is used to represent the alphabet, and a language L over the alphabet decide whether or not W belongs to L. This is the membership problem. So for example, I am taking the word, W is nothing but the word or string, whatever it is, word or string or same. So here my string is 100011. So this is the given string. So I have to check whether this particular string belongs to the language L over the alphabet sigma. Okay, we have to check whether this particular string, what a string? String is nothing but the collection of alphabets. So here the alphabet, it consists of 0, 1 alone. So in this membership problem, no, we have to check whether this particular string belongs to the language over the alphabet. Belongs to the language L over the alphabet sigma. So this is the membership problem. Okay. And then, so now we are entering into our subject. So before this, we studied the basic elements or basic concepts of our TOC. That is string, what is language, and then what is alphabet. So how to form the language from the given statement, and then how to check whether the given string is belongs to the particular language over the alphabet. So these are all the basic concepts of finite automata. Now we are entering into our subject, finite automata. So here we have so many applications of finite automata or theory of computation. So some of the applications are the software for designing and checking the behavior of digital circuits. Any digital circuit, no, it may be on, off switch, whatever it is, any digital circuit. So using our finite automata, we can design a software and check the behavior of the digital circuit. And then coming to the second application, it is nothing but the lexical analyzer of the compiler. So we know that the compiler is nothing but the translator, which translates the higher level language into the lower level language. So what is higher level language? Which is nothing but the C language or C++. So whatever it is, it should be in user understandable format, no, which is known as the higher level language. The purpose of compiler is it translates the higher level language into the lower level language. So what is lower level language? Which is nothing but the machine understandable language, which is zeros and ones alone. So what is the purpose of compiler? It converts the higher level language into lower level language. In compiler, no, we have n number of many phases are there. In that, the first phase, no, which is nothing but the lexical analyzer phase. For this lexical analyzer, we should use finite automata. Designing a lexical analyzer, no, we should use finite automata. So what is lexical analyzer? Recognizing the tokens alone. So recognizing the tokens alone, that is the lexical analyzer. So in this lexical analyzer, designing a lexical analyzer, we are using the finite automata. So coming to the third application, software for scanning large bodies of text. Okay. So for example, we want to find something from the Word document or something from the presentation, that is PPT, whatever it is, all those search options, no, we have to use finite automata. While designing the searching engine, searching machine, no, we have to use finite automata. And then the next one, software for verifying system of all types that have a finite number of states. So example for this software is stock market transaction, communication or network protocol, etc. So now coming to the finite automata. So now consider the example on off switch. So in everyone, no, we use the switch first. If it is in on state, now we can switch off the switch. If it is in off state, now we can on the switch. Okay, so which is nothing but the digital, any type of digital circuit. No, this finite automata is used to design the digital circuit as well as check the digital circuit. So here first we have to design the digital circuit or any circuit here. So here this is nothing but the on off switch. In this diagram, no, this particular diagram is a simple finite automata. Simple finite automata. In this we have two circles, no, which is nothing but the states. Two circles. The first one labeled as off and then the second one is labeled as on. So these two circles are known as the states of the finite automata. So in this, no, see the first state, one arrow symbol followed by one circle. So this is nothing but the start state. That is the initial state of this particular model. Okay, and then we have two different edges. So edge is nothing but the arrow from one state to another state. So that is the edge, no, which is labeled by some operation. Okay, so see, push is one of the operation. So again, push is the another operation. So what is the purpose of this operation? So based on the current state and then the current operation, we can decide the next state. Okay. So what is current state? So see, initially we are in off state. Off now, the particular switch is in off. Okay. And then performing the push operation. That is, push means pressing the particular switch. Okay. So based on the current state and then current operation, we can reach the next state as the output. So what is next state? On. See, if it is in off state now, while pressing the particular switch, it is in on state. Okay. So if it is in on state, we are performing the push operation now, it goes to the off state. So this is the simple example of our finite automata. So this is a graphical representation. So likewise, we have to write the code. So this is for hardware. If it is in software, now we have to write the code for this particular operation. So how to write the code? So based on the initial, based on the condition, based on the state, and then based on the operation. So current state and current operation, we can decide the next state. Okay, likewise, we have to write the code. So see, this is the action here, and then the circle which is used to represent the state, and then modeling recognition of the word then. So this is for then. So see, in our higher level language or any high level language, we are using the set of keywords. Okay. So here, this is one simple model which recognize the keyword then alone. Okay. So see, in Python, no, we are using the word then. This is nothing but the keyword. So see, circle which is used to represent the state. So here, which is the initial state, one arrow symbol, small arrow symbol followed by the circle, which is known as the start symbol or initial state. Initial state. Okay, wow. So coming to the last circle. So see the last circle, we have two circles, double circle. This is nothing but the double circle, which is nothing but the accept state or final state. Final state or accept state. So any string, what is string? It is a collection of alphabet. Any string, we have to process it from the start state. Okay, till final state, you have to process the string. If we reach the final state, means then the string is valid string. Okay, if we cannot reach the final state, now the string is an invalid string. So the particular machine is rejected the string. So for example, here then is the keyword. Okay, this is the model for then. So first you have to read the first symbol of the then word. What is the first symbol? T. Initially, we are in the initial state. Initial state and then the input T. So based on initial and input symbol, we can decide the next state. Okay. So if it is T, we can change the state from initials to the next state. So instead of then, instead of T, here we use the capital D, means the string is rejected by the model because we cannot change the state. Okay. If it is T, means we can change the state. If it is other than T, means we cannot change the state. Okay, likewise, in the next, after processing the T, what is the next symbol? H is the next symbol. So now currently we are in the second state, and then this input symbol H, then the string is, the particular symbol is accepted. No, if it is H now, then we can change the state. And then what about third one? E. This is also a valid symbol, no? So we can change the state. Likewise, N is also a valid symbol. We can change the state. So what we have to do finally, if we reach the final state, then the string is accepted. Otherwise, the string is rejected by the mathematical model or a finite automata. So this is the basic processing of finite automata. Okay. So now coming to the informal and formal representation. So what is finite automata? It is the simplest machine to recognize pattern. So any pattern, if it is a parenthesis matching, or if it is any string we want to accept, or any design a machine for any pattern, we need finite automata. It is the simplest machine. Okay. What is the other name of finite state machine? Finite automata, which is finite state machine. This is the finite state machine, or FSM is the other name of our finite automata. And then what about the next one? Finite automata takes the string of symbol as input and it changes its state accordingly. When the desired symbol is found, then the transition occurs. At the time of transition, the automata can either move to the next state or stay in the same state. If it is a valid symbol, the finite automata move to the next state. If it is an invalid symbol, no, stay in the same state. So this is the basics of our finite automata. And then see, this is a model. This is a mathematical model. So see here, we have one input file. This input file is used to store the string or alphabets, whatever it is. This input file is divided into cells. So each cell can carry a single symbol. Okay, this is the input file. So from this input file, we have a control unit to read the symbol. It generates the output. So what is output here? It is simply accepts the given string or reject the given string. That is the output of the finite automata. So as I told, no lexical analyzer, while designing a lexical analyzer of our compiler, no finite automata is used to recognize the languages, recognize the keywords, recognize the words, whatever it is, only recognition. Okay, so recognize the string means what? It is just to check the pattern alone. For example, if it is an identifier, so identifier means the first character should be an alphabet, followed by any number of characters or numbers are allowed. Okay, these are we have some set of rules, no? So according to those rules, we have to design the mathematical model for our lexical analyzer. So what about the output? Whether the given string is accepted or not. That is the output of our finite automata. And then coming to the informal definition. So this is the formal definition of our finite automata. It is nothing but the five tuple. It is a collection of five tuples. So what is the first one? First one is the capital Q. Capital Q is nothing but the finite set of states. So in any machine, we have set of states, and then these states are joined with the help of edges. No, so circle is used to represent the states. So here capital Q is nothing but the finite set of states. So and then as we know that the sigma summation symbol, no, which is used to represent the alphabet. Q0 and then third parameter, no, Q0, which is nothing but the initial state. And then capital F, which is nothing but the final state. And then we have one symbol, no, this is the transition function. So transition function, which is used to change the state from one state to another, change from one state to another. That is the purpose of our transition function. So how we can change the state? Based on the current state and then the current input symbol only, we can change the state. So that this particular transition function accepts two parameters, that is current state and then the current input symbol as an input. It generates the next state as the output. Okay, so we have five parameters. Don't forget, in finite automata, we have five parameters. So coming to the next higher model push down automata, we have seven parameters. And then the next higher level Turing machine, we have the seven parameters. So don't forget, in finite automata, it has only the five parameters. That is capital Q is the set of states and then alphabets, transition function. So in transition function, it accepts current state and the current symbol as the input. It generates the next state as the output. So here Q0 is the initial state and then capital F is the final state. So coming to the types of finite automata, we have deterministic finite automata or DFA, non-deterministic finite automata or NFA. In NFA, we have one more variant, that is non-deterministic finite automata with epsilon transition. This is another variant of our NFA. So basically, the finite automata is divided into two: deterministic finite automata and then non-deterministic finite automata. So ENFA is nothing but the variant of non-deterministic finite automata. So coming to the deterministic finite automata. So what is deterministic finite automata or DFA? So here we have a determined path for a particular input symbol from the current state to the next state. That is DFA. Okay, we have a single path. Determined path means what? We have a single path for a current input symbol from current state to the next state. That is deterministic finite automata. What about non-deterministic finite automata? In non-deterministic finite automata, for a particular input symbol, we have more than one path. We have more than one path. We cannot determine a path. We cannot determine a particular path for the current input symbol from the current state. Okay, that is non-deterministic. In deterministic, there is a single path. In non-deterministic, there is more than one path for a particular input symbol from the current state. That is DFA and NFA. Am I clear? Yes. So here we have two kinds of representations are there for DFA. First one is the transition diagram, which means graphical representation. And then the next one, transition table representation, which table means we know that the columns and the rows, no, we have to represent the DFA with the use of table. Okay, two different kinds of representation, transition diagram and then the transition table representation. And then the formal definition no DFA there is no change. Okay, that is set of states and then alphabet. Q0 is the initial state, F is the final state, and then the transition function. It accepts capital Q and alphabet. What is capital Q? Which is nothing but the current state, and then alphabet means which is the current input symbol. So based on these two values, okay, this DFA will decide the next state. So this is the formal definition. And then, so see, this is the example of our DFA. So Q1 is the initial state, Q2 is the final state. So as we know that the arrow followed by the circle means which is used to represent the initial state. If it is double circle means which is used to represent the final state. And then we can join the states with the help of edges with some labels. So here what is the label? A is the label. Okay, this is the graphical representation or transition diagrammatical representation of our DFA. Okay, which is nothing but the graph, directed graph we are using for designing the finite automata. We are using the directed graph in this vertices, which is for states of finite automata, and then edges, no arc, that is directed line from one state to another state. Directed line from one state to another state, which is nothing but the edges with some label, which is used, which is nothing but the transition. Okay, so this is the example of our DFA. So see, for a input symbol A, there is only one path from current state to the next state. We have a determined path from current state to the next state. This is DFA. Okay, and then the another representation is there, no, which is transition table representation. In this table, we have set of rows and columns. So rows, which is used for states. In columns, now we are using inputs. So in my alphabet, I have 0, 1. In column, I have to write 0, 1. I have three different states here. That is S1, S2, S3. Okay, S1 is the initial state and then S2 is the final state. So the entry, what about the entry of that particular table, which is nothing but the next state. So how will you decide the next state? Based on the current input symbol and then the current state, we can decide the next state. Okay, two different representation. So this is another example of DFA. So see here, DFA means we have a determined path. So now consider the state Q0 alone. We have two inputs. Okay, so now consider the value 0 alone. From Q0, we have only one path, that is Q0 to Q2 alone. We have a determined path for a input symbol 0 from Q0. Okay, now consider the symbol 1. No, we have a determined only one path. Determined path means what? Only one path from current state to the next state. So what is current state here? Q0 is the current state and then 1 is the current symbol, which is the next state. Q0 is the next state. Okay, we have a determined path means deterministic finite automata. We have more than one path now, which is non-deterministic finite automata. Okay, what does a DFA do on reading and input? So we have input. Input is nothing but a word. What is word? It is a collection of alphabets. Okay, is W is accepted by DFA or not? So first we have to start from the start state Q0 and then start from the first symbol of the word. So based on current state and the current input symbol, it will decide the next state. Okay. So likewise, we have to process all the symbols. At the end of the string, no, we should reach the final state. If we reach the final state means then the string is accepted. Otherwise, the string is rejected by the finite automata. Okay. And then what is regular language? So regular language, which is nothing but the language for our finite automata. Okay. Let L of A be a language recognized by a DFA. Okay. Then L of A is known as the regular language. A regular language is a language which is recognized by the finite automata. So we can locate the regular language in the Chomsky hierarchy. So in that, no, we have regular languages. Under that, we have a mathematical model, finite automata. So this is the Chomsky hierarchy. So see here, this is the innermost circle, innermost oval is there, no? That is the regular language, and its equivalent mathematical model is nothing but the DFA. So now coming to the example for our DFA, build a DFA for the following language. So here, what is the condition? The language, it consists of set of strings. Set of strings, here W is used to represent the strings or words. The condition on particular word W is a binary string. So binary string means we can decide the alphabet here 0, 1 that contains a 0, 1 as a substring. So on each and every string in this particular language, no, it contains 0, 1 as a substring. So see, steps first we have to decide the set of states and then decide the transition function, final state. Double circle now, which is the final state. A single circle means which are all the non-final states, and then we have only one start state. So how will you identify the start state? One arrow symbol followed by the circle, which is used to identify the start state. Okay, and then this is the DFA that starts with Q0. What is the minimum string of this particular language? 0, 1 is the minimum string. Okay, it should not contain epsilon because epsilon is the null string. But the given condition is all the string of this particular language contains 0, 1 as a substring. So the minimum string is 0, 1, and then the followed by starts with any number of zeros or any number of ones, but it should contain a 0, 1 as a substring. So this is the final diagram. We have three different states. So you have to mention capital Q equal to Q0, Q1, Q2. And then this is the binary string. No, we know that the alphabet equal to 0, 1. Here arrow followed by circle, which is the initial state, so that the Q0 is the initial state. And then double circle now, which is the final state, so that the Q2 is the final state of this given DFE. Okay, and then we can draw the transition table. So in rows, we have to write a set of states. In columns, we have to write symbols. So a set of states now Q0, Q1, Q2. And then in columns, you have to write 0, 1. Those two are the input symbols here. Okay, what about the entry? So based on current input and then current state, we have to decide the next state. So see here, Q0 is the initial state and then 0 is the input. So we have to see the diagram. Q0 is the state and then 0 is the input symbol, which is the next state Q1. So you have to write Q1 here. Q0 is the state and then 1 is the symbol. So we can reach Q0 itself. Okay, so here you have to write Q0. So likewise, you have to fill all the cells of this particular transition table. So this is DFA representation. We have two different representation, that is transition diagram representation and then transition table representation here. What makes this DFA deterministic? Deterministic means see the entry of the table. So each cell, no, it contains only one state as the output, right? If it is more than one means what? We have more than one path for a specific input symbol from the current state to the next state. Okay. If it is a single entry, it is deterministic. If it is more than one state in a single cell, it is a non-deterministic. And then coming to the non-deterministic, as we know that the uh, definition of a non-deterministic, that is informal definition. Informal definition means what? We have more than one path for a specific input symbol from current state to the next state, which is known as the non-deterministic finite automata here. Okay, so see, Q1 is the initial state. Consider the input symbol 1. We have more than one path. That is Q1 and then Q2. We have more than one path for a particular input symbol. So we cannot determine a single path for a specific input symbol from the current state. So that this is the non-deterministic finite automata. And then coming to the formal definition of NFA. Okay, NFA or a formal definition, we have again 5 tuples. Q is the final set of states. And then this is the alphabet finite set of input symbols. Q0 is the initial state. F is the final state. And then we have a transition function. Here also the transition function which accepts 2 inputs, that is capital Q, which is the state, and then current input symbol. But what about output? It is a subset of Q. So if it is a subset, means the output may contain more number of states. That is the difference between NFA and the DFA. Okay, how to use an NFA? Again, same thing. They are giving some input. Input means which is nothing but the word. And then check whether the given string is accepted by the non-deterministic finite automata or not. We have to follow the same rule. That is initially start from the start state with the current input symbol. We have to reach the next state and then process the next input symbol, etc., etc. Up to end of the string, we have to process the string by using our designed finite non-deterministic finite automata. So now, so see the same problem, that is DFA. No, in DFA, the set of strings contains 0, 1 as a substring. So here we have NFA. So see the diagram. Here itself we can form 0, 1. Okay, and then here 0, 1, 0, 1. So see here current state, we consider the initial state Q0 and then the current input symbol 0. We have more than one path. So either we can reach Q1 or Q0 itself. Q0 itself or Q1 with the input symbol 0. So we have more than one path. This is non-deterministic finite automata and it's equivalent table representation. So see the entry of this table in this, in the first cell, that is Q0, 0, we have 2 states as the output. That is Q0 and Q1 as the output here. Okay, if it is more than one state in particular entry, now this is not deterministic. If it is a single state in each cell of the table, now which is deterministic. Okay, now coming to the differences. All DFA and NFA. What is the first difference? All transactions are deterministic. Here, some transactions could be non-deterministic. And then the next one, for each state, a transition on all possible symbols should be defined. Not all symbol transition need to be defined explicitly. That is NFA. The third step, no, it accepts input if the last state visited in F. The same thing for acceptance, no, we have to follow the same rule for DFA and NFA. Okay, accepts input if one of the last state is in F. What is capital F, which is nothing but the final state. Sometimes harder to construct because of the number of states. So generally, NFA is very easy to construct from for the any given languages. Okay, so these are all the differences. And then coming to the application, as we discussed earlier, first one, text indexing, finding the pattern, extension of idea, whatever. These are all the basic applications. A few of operations of DFAs and NFAs. The machine never really terminates. Okay, these are all the properties of NFA and DFA. The machine, NFA, FA means what? It is a machine. Okay, this machine never really terminates. It is always watching for the next input symbol or making transition. Okay, it always looking into the next input symbol or making some transitions. It never terminates. That is the first basic property. And then coming to the second one, the machine decides when to consume the next symbol from the input and then when to ignore it. So this particular machine has the capability to decide to accept the next input symbol or to ignore the symbol. Okay, but the thing is, this particular machine can never skip any symbol. And then coming to the transition can happen even without really consuming an input symbol. If this happens, then it becomes the ENFE. Okay, so we'll discuss the epsilon NFE. That is epsilon NFE. Epsilon means what? We know that the null string. So epsilon is nothing but the null string. So this finite automata, we can allow explicit transition. Okay, by using epsilon, which means without reading any valid input from this string, we can change the state. Okay, without reading any input, we can change the state with the help of this null string value. Okay, that is a transition from one state to another state without consuming any additional input symbol. So what is the purpose of this E transition, epsilon transition? It makes easier to construct FE. It is very easier to construct any model. So see the example, again same example, W is empty or if non-empty will end in 0, 1. So if it is empty, you can include epsilon. Okay, you can include epsilon also. So see the table. So see here, we have more entries now. This is nothing but the NFE. Okay, and then while writing the columns, first column, it is for 0. And then second column, it is for the input symbol 1. And then the third column, you have to include one extra column for the input null. Okay, null string, you have to make one extra column. Okay, because this is epsilon NFE. So see in this, without reading any input, because we have the alphabet 0, 1 alone here. Okay, so see this first state q dash 0. We have q0 dash. So from this, without reading any input, any valid input, we can change the state. Simply we have to change the state without reading any input, means we have to use null string, which is epsilon. So in transition table, we should include epsilon also as a input. And then, so what is E closure? What is epsilon closure? Which means we have to include that self state plus epsilon reachable states. Okay, we have to include self state and then epsilon reachable states you have to include. That is the E closure or epsilon closure of any state. So E closure of state Q is the set of all states that can be reached from Q by repeatedly making an arbitrary number of transitions. Okay, and then that's all about the finite automata. That is, so we discussed what are the basic elements of finite automata, and then what is FA, and then what is formal definition and informal definition of finite automata, and then what are the representations are there, types of finite automata. We have two types, DFA and NFA. In NFA, we have one more variant, that is epsilon NFA, and then how to process the input in all the types, all its types, no, DFA, NFA, and the ENFA, and then how to construct the finite automata for the given language, and then how to draw the table. We discussed all those things. Okay. So next we discuss some gate questions here. So see the first question. What is FSM? Finite state machine. This is the another name of our finite automata. Okay. So initially we discussed to know what is the other name of finite automata, which is finite state machine. So this is the machine we have to decide the language. Okay. So this is the language for increments a given bit pattern by 1. Okay. It increments the given bit pattern by 1. This is the finite automata. So what we have to do first, we have to write the language. That is, increments a given bit pattern by one. Now, first you have to write all possible strings in the language. After writing the strings, first you have to design this finite automata for the initial string, that is first string. After that, we have to do the same process for the forthcoming strings. Okay, so that the result is this finite state machine which accepts the values that increments a given bit pattern by 1. And then the second question, a finite state machine can be considered to be a Turing machine of finite tape length. So the answer is without a rewinding capability. What is rewinding capability? Rewinding capability means reading a reverse direction. Okay. In finite automata, we can move the control head in forward direction alone. We cannot move the reverse direction. So without rewinding capability and the unidirectional tape movement alone. Okay, so A is the answer here. Finite state machine can be considered to be a Turing machine of finite tape length without rewinding capability and unidirectional tape movement alone. And then the next one. Palindrome cannot be recognized by finite state automata because. So we have 4 options here. Palindrome means what? While reading from the backward, no, it gives the same meaning. That is the palindrome. Okay, but we cannot design the finite state automata for palindromes because in finite state machine, no, we don't have any memory unit. Okay, memory unit we don't have in finite automata, so that we cannot remember anything. If it is palindrome, the first symbol and last symbol should be same. No, we have to remember the first symbol, then only we can check whether the last symbol is same as the first symbol. Okay, but in finite automata, no, we don't have memory. So what is the first option? Finite state automata cannot remember arbitrary large amount of information. This is true. And then coming to the second option, finite state automata cannot deterministically fix the midpoint. Okay, if we want to remember something, it means we can fix the midpoint. But in this, we cannot remember anything, means we cannot fix the midpoint. So this is also a true. Even if the midpoint is known, and finite state machine cannot find whether the second of the match is the first of. As I told, no, it don't have memory. So if it has memory, now we can perform all these 3 kinds of operation on finite state machine. Okay, we want to remember something, we want to set the midpoint, we want to check whether the first of is equivalent to the second of. We cannot do all these 3 operations. So that the answer is all the above. D is the correct option. Okay, palindromes. Using our finite automata, we cannot design a palindrome. And then the third question, a DFA can be expressed as a phi tuple, that is Q alphabet transition function Q naught F. The transition function defines as we know that it accepts the current state and the current input symbol as the input, and it gives the next state as the output. So here D is the option. D is the correct answer. So see, first one, based on current input alone, it doesn't give the output value. So 2 states, which is not applicable for our transition function of finite automata. Okay, so here D is the correct option because the transition function of finite automata accepts 2 parameters. First one is the current state, and then second parameter is the alphabet. It gives the next state as the output. So the correct answer is D. Then coming to the next question, the number of states required by the finite state machine to simulate the behavior of the computer with the memory capable of storing m words. So each m word, the length of each word is n bits. So we have to decide the number of states, total number of states of this finite state machine. Okay, so see, if the string consists of n bits alone, now we need 2 power n states. Okay, that is the general formula for every finite automata. If it is n bit string, means we need 2 power n number of states. Okay, so but in the given problem, no, it consists of m words, and then the length of each word is n bit. So that the total number of states, no, we should multiply m with n and then 2 to the power of mn. That is the correct answer. So here C is the correct answer. So totally we need 2 to the power of m into n number of states to design the finite state machine for this given language. So next one. The following finite automata recognize which of the given language. So see this here, A is this A, B, C are the states. A is the initial state and C is the final state. And then how will you reach the final state? Reading 0 and 1. 0, 1, I can reach the final state. Okay, 0, 1, I can reach the final state. Again, 0, 1, I can reach the final state. Okay, that means the end of the particular string, it should be 0, 1. That is, it accepts all the strings ends with 0, 1. Accepts all the strings ends with 0, 1. So at each string, it contains 0, 1 at the end. Okay, so that A is the correct option here. So initially it may contain 0 or 1, whatever it is, but end of the string, it should be 0, 1. So here A is the correct option. Consider the following deterministic finite automata. So here the given DFA is there. Let denote the set of 8-bit strings whose second bit and then third, sixth, seventh. So totally 4 bits here we have to apply the condition. In second bit, it should be 1, and then third bit, it should be 1, and then sixth bit should be 1, and then the seventh bit should be 1. So this is the 8-bit string. So this is the finite automata or DFA for 8-bit string. Okay, but the given condition is second, third, sixth, and the seventh bits are 1. So according to this condition, totally we have 2 strings are accepted by this particular machine. Only 2 strings are accepted by this machine. So see those strings 0, 1, 1, 1, 0, 1, 1, 0. The another string is 0, 1, 1, 1, 0, 1, 1, 1. Okay, these 2 are the valid string for this particular machine. And then the next question. So see here, 2 finite state machines are said to be equivalent if the first option is have same number of states, have same number of edges, have same number of states and edges. The option recognize the same set of tokens or same set of input string. Okay, so here the 2 finite automata are said to be equivalent if they recognize the same set of input symbols or same set of strings or same set of tokens. So D is the correct option. And then the next one. So here let n be an NFA with the n states. Let k be the number of states of minimal DFA which is equivalent to n. Which of the following is the correct answer? Okay, so here NFA and then minimize the DFA. So how to convert the NFA into DFA? We have the formula, right? So using those formula, we need to convert the given NFA into DFA. Okay, so after that, after converting the NFA into DFA, we need to find the minimized DFA. So minimized DFA means we can, if our DFA consists of more number of states now, according to some condition, we can reduce the number of states. So we can reduce the number of states. We have so many methods are there for minimized DFA. In next class, we will discuss the minimized DFA. Okay, which is equivalent to n. Which one of the following is necessarily 2? So what is k? K is nothing but the set of number of states of minimized DFA, but in NFA, the state should be 2 per n. because we know that the number of states required for NFA is equivalent to the length of the word, length of the string. Okay, so if the length of the string is n, means we need 2 per n number of states to design the DFA or NFA. Okay, so here k is nothing but the number of states in minimized DFA. The first option, no, in minimized DFA, the number of states, it should be greater than or equal to 2 power n, or k greater than or equal to n, or k less than or equal to n square, k less than or equal to 2 power n. So what is minimization? Minimization means what? We are going to reduce the number of states alone. So number of states, now here k, it should be less than or equal to 2 power n. Okay, if we cannot minimize the given DFA, we can take it as it is. Okay, for example, if our DFA contains some 7 states, we cannot minimize we cannot apply the condition for minimizing the given DFA, means after minimization process also will be getting the same 7 set of states alone. Okay, so the set of states in minimized DFA should be less than or equal to 2 power n. What is 2 power n? Here 2 power n is the number of states required to design a DFA or NFA for any given string with the length n. Okay, and then you have to practice all this type of questions now. Okay, okay, thank you, students. Thanks for listening. So don't forget, you have to practice with more problems. Okay, thank you so much.